There's an invisible force that pretty much runs every single moment of our lives. I mean, it's so powerful that without it, you couldn't walk. Cars couldn't stop. The world as we know it would just fly apart. Today, we're going to pull back the curtain and put a name to that force: friction. Okay, let's start with something we've all felt. You ever try to push like a super heavy box across the floor? That first shove takes a ton of effort, doesn't it? But then, once you get it going, it gets a little easier to keep it moving. So, why is that? Or picture this, a soccer ball rolling across a field. What's the invisible hand that reaches out and slows it down to a stop? Well, the answer to both of those puzzles is exactly the same thing. It's this invisible, ever-present force that resists motion. But, and here's the crazy part, it's also the very thing that makes motion possible in the first place. Yep, that force is friction, and that's what we're going to dive into today. All right, so what exactly is this force? To really get it, we've got to zoom in, and I mean way in, all the way down to the microscopic level. So you look at a tabletop or maybe a polished floor, and you'd think, yeah, that's perfectly smooth. But if you could zoom in with a super powerful microscope, you wouldn't see a flat surface at all. You'd see this rugged landscape of peaks and valleys, like a tiny invisible mountain range. And friction, well, it's basically what happens when you try to drag one of these microscopic mountain ranges over another one. And this resistance, it really boils down to two main things. First, you've got that surface roughness we just talked about. Those little microscopic teeth on each surface are literally catching and locking into each other. But then on top of that, there's also something chemical going on: molecular adhesion. See, at the tiniest points where the surfaces actually touch, their atoms can form these little temporary bonds, kind of like a stickiness. So it's this mashup of physical grabbing and chemical sticking. And you know science, of course, there's a formula to measure all this. It looks like F equals mu times N. Don't worry, it's pretty simple. F is just the force of friction we're trying to figure out. N is what's called the normal force, which is really just a fancy way of saying how hard the two surfaces are being squished together. For our box, that's basically its weight. And that little Greek letter, mu, that's the cool part. It's the coefficient of friction. It's just a number that tells you how grippy or how slippery two surfaces are when they're together. Okay, but here's where it gets really interesting. It turns out not all friction is the same. It actually has two totally different personalities, two faces that you and I deal with every single day. First up, you've got static friction. I like to call this the stubborn one. It's the force you have to fight just to get something to start moving. And what's wild is that it's not a fixed number. It actually matches your push. You push a little, it pushes back a little. You push harder, it pushes back harder, right up until you hit its breaking point. And it's stronger because those little mountain ranges have had time to settle in and really get a good grip. But once you break that grip, you switch over to kinetic friction. This is the sliding force, and it's always just a little bit weaker, because now the surfaces are kind of just skipping and bouncing over each other, never getting a chance to lock in again. And boom, that right there is the answer to why it's so hard to start pushing that heavy box. And this difference between static and kinetic friction, it's not just some textbook idea. It's the exact reason a critical piece of tech in your car works. I'm talking about anti-lock brakes, ABS. Think about it. A skidding tire is sliding, right? So it's using that weaker kinetic friction. But a tire that's gripping the road is using the much stronger static friction. So the whole job of an ABS system is to cleverly keep your tires right in that sweet spot of maximum grip, the static zone. So how does it pull that off? Well, it's like this incredibly fast dance. The second a sensor feels a wheel starting to lock up and skid, the system starts pulsing the brakes. It rapidly lets go of the pressure, then grabs again. That tiny moment of release is just enough to let the wheel spin a little and regain that powerful static friction, that amazing grip, before it breaks again. And this all happens dozens of times a second, basically keeping you right on the very edge of control without ever letting you go into a full-blown, uncontrolled skid. So, up to this point, friction sounds like our best buddy, right? It's keeping our cars on the road, it's letting us walk around, but it's not quite that simple. You see, friction is both absolutely essential for our survival and a huge headache for engineers, which brings us to its dual nature. Is this thing a friend or is it a foe? I mean, just take a look here. On the one hand, in the good column, friction is the absolute hero. It's what allows us to walk without slipping all over the place. It's what makes our brakes work. It's what holds a nail in a piece of wood or a knot in a rope. But then you look at the bad column, and suddenly it's the villain. It's the force that causes parts in an engine to wear out, that produces all this unwanted heat, and that just robs our cars of fuel efficiency. So, what do we do about the bad side of friction? How do we manage this foe? Well, we fight it with lubricants. Just think about motor oil. Its entire job is to squeeze in between the metal parts of an engine and create this super thin, slippery film. That little buffer keeps our microscopic mountain ranges from grinding directly against each other, which massively cuts down on wear, tear, heat, and all that wasted energy. And this really brings us to the main idea here. When it comes to friction, our relationship with it isn't about just getting rid of it or trying to have as much of it as possible. It's all about managing it. It's this constant, delicate negotiation. And that right there is the central paradox, isn't it? Friction is this constant tug of war. We absolutely depend on it to grip the road, but at the same time, we're fighting it tooth and nail inside our engines. It's the one force that wants to slow everything down, but it's also the only force that lets us get moving at all. So the next time you take a walk or drive your car, or even just pick up a glass of water, I want you to think about that invisible force. Remember that you are in a constant, delicate negotiation with every surface you touch. You're balancing grip with glide, hold with release. And once you really understand this invisible brake and this invisible engine, it kind of changes how you see everything. So the only question left is, what are you going to do with that understanding?